Now we're going to go on to 11.2, inference from relationships. So I'll read this section and we'll talk about it a little bit. It says, review of categorical data and their relationships. Example, Penn State has its main campus in the small town of State College and more than 20 smaller satellite Commonwealth campuses around the state. Penn State's Division of Student Affairs polls separate random samples of undergraduates from the main campus and all the Commonwealth campuses about their use of online social networking. Facebook was the most popular site with more than 80% of students having an account. Here is a comparison of Facebook use by undergraduates at the main campus and surrounding Commonwealth campuses who have a Facebook account. So if we're just kind of looking at the data, they sampled 910 people at the main campus and 627 people at different Commonwealth campuses in total. So, on the main campus, 55 out of the 910 use Facebook several times a month or less. 215 out of those 910 did it at least once a week, and 640 at least once a day. Similarly, over here at the Commonwealth campuses, they gave us raw counts. So number one, it says calculate the conditional distribution in proportion or percent of Facebook use for each campus setting. So when I'm looking at this data, I'm going to be looking down for each different campus setting. Let me do it in two different colors so we can understand it a little bit more. All right. So if I think about on the main campus, how many people on the main campus used Facebook several times a month or less? So we're just going to take that 55 and divide it by this 910. So that would be a conditional probability. Okay, so 6.04%. Okay, so 6.04% of those surveyed on the main campus use Facebook several times a month or less. Let's do the same thing for this one. So we'll do 215 divided by 910. So that would be 23.63%. And then we'll take the 640 and divide it by 910. It says 70.33. Now let's do exactly the same thing with the Commonwealth campuses. All right, so I'm going to take 76 divided by 627. All right, 12.12%. All right, now we're going to take the 157 divided by 627, 25.04%. And we'll take the 394 divided by the 627, 62.84%. In part 2, it says, why is it important to compare proportions rather than counts from question 1? So if we're just looking at raw numbers, okay, for instance, if you look at this number compared to this number, you could say, oh, wait, there's so many more people on the main campus that use Facebook at least once a day than the Commonwealth campus. And while that's true, it's all based on relative sample size. We've asked more people at the main campus. So when we compare by percents, it's more of an apple-to-apple comparison, just like a z-score is an apple-to-apple comparison. Okay, so when we look at relative percentages, okay, or conditional percentages here, it gives a more accurate way to compare. Okay, so that's why we don't want to just look at counts if we're comparing things. If we look at relative percent, we can see it's going to be easier to see any major differences. Okay, so number 3, it says looking at the conditional distribution percentages, so these things right here and these things right here. All right. Comment on any similarities and differences between the two campus settings. Based on your responses, do you think that location, okay, which is the campus setting, and the use of Facebook are independent or not? Okay. So if I kind of look across, these are fairly close to each other. Look at those 2%. Okay. They're within about 1.5 points of each other. Where the real differences happen, okay, there's a big difference there. This is about twice of that. And this is a pretty big jump too. I mean, that's 8 percentage points of difference. Okay, so I might want to comment on that. So we can say something like the relative percent of Facebook use at least once per week. I'm talking about the middle row, and this one is about the same in both campus settings. And then I can comment on some differences. I can say in the Commonwealth campuses, students are more likely, okay, because this number is bigger than that number, to only use Facebook several times a month or less. And then we can even be specific, and we can say 12.12% in Commonwealth versus 6.04% in main campus. Okay. So in the Commonwealth campuses, students are more likely to only use Facebook several times a month or less, 12.12% versus 6.04%, and a little less likely to use Facebook at least once per day. Once per day. I can say 62.84% versus 70.33%. Okay, so something like that. It says, based on your responses, do you think that location, setting, and use of Facebook are independent or not? So, if these things are really independent, if use of Facebook and location are really independent, we expect these percentages to be fairly close to each other in each case. This one's kind of tough. Okay, are these close enough to each other? Or is there major differences? Okay, I still think they're relatively close to each other. I mean, 6%, yeah, it's a lot. Okay, but you're not, this isn't like 25% and this is 6%. Okay, and this isn't like 50% and this is 80%. There are some differences, but to me, it's not quite drastic enough, okay, to believe that these things are not independent. Or excuse me, to believe that these things affect each other. Does location and use of, are they associated? That's the best way to think about it. Are those associated in some way? I would say, no, not really, okay? No, not really. Okay, so I would argue, my argument would be, all right, they are independent. So in other words, if these are close enough to each other in each case, then those things would be independent. the use of Facebook is independent of location. Okay. So, why do we bring this up? Okay. Because this is the basis of the chi-square test for homogeneity and independence. There's two different chi-square tests that we haven't talked about yet. There's three in total. So we have the chi-square test for goodness of fit. We talked about that last time. And today we're going to learn about the chi-square for independence and the chi-square for association. Okay, that's what we're talking about today. All right, so our process of going through this chi-square hypothesis test, same as before. We're going to do a statement about the hypothesis. Okay, we're going to do our three conditions for the condition check. All right. However, the expected counts, the formula is going to be a little different. It's going to be this right here. We'll get to that in an example. Okay, we're going to do some calculations. We're going to calculate the chi-square test statistic. Okay. However, the degrees of freedom with the goodness of fit in the test, it was simply number of categories minus 1. Now it's going to be a little bit different. So that's what's going to be a little bit different. Okay, we're going to make our decision. All right, compare the p-value with your alpha. Okay, so it's going to be linkage. All right, and then we conclude. So same type of steps as before. Same types of steps as before. So, how do we state our hypotheses for these two types of tests? Well, if it's a test of homogeneity, we're going to do the test for homogeneity when we have 2 plus populations. Okay, but independence, we're only going to have 1 population. That's the main difference. Okay. And you'll phrase them something like, the null hypothesis for homogeneity would be, the variable of interest is the same for all populations, but we're going to use it in context. And the variable of interest is not the same for all populations, again in context. In the test for independence, we can phrase it one of a couple of ways. We can either use the word independence or the word association. Okay, I think independence is easier to think about. All right, so in independence, variable 1 and variable 2 are independent. You're going to assume they are independent, that there is no connection or there's no association between them. And we need enough evidence to show that they're not independent. They affect each other, okay? Or they're associated with each other. All right. The 3 conditions, they're the same. All right. And then our calculations and conclusions. It says the calculator will apply the same formula used in the goodness of fit for each cell of the matrix and then add the results together to generate the chi-square test statistic for these tests. Be sure to record the chi-square test statistic, the p-value, and the degrees of freedom. So there's a little section in your notes here about the calculator help, but rather than just read that verbatim, let's just jump right into an example because it's easier to figure out when you actually do it. All right. So it says the counseling unit of Woodrow College is interested in the relationship between anxiety level and the need to succeed. So the need to succeed variable is down. All right, down there, they're in rows. And the anxiety level is across the top. High, medium, low, up there. So those are 2 different variables, but it still comes from 1 population. All right, and it's 2 variables. And each variable has multiple categories. 1 population, but 2 variables. So this would be a chi-square test of independence because the data is coming from a single population, the students at 1 college. All right, so it says a random sample of 200 college freshmen was taken. So my total here is going to be 200. All right, the freshmen were given tests to measure their anxiety level and their need to succeed. Question is there evidence that anxiety level and the need to succeed are dependent, which would mean not independent? Go through the complete hypothesis test. Well, before we get to the hypothesis test, let's actually go ahead and sum these things up. So let's just add down. 30 plus 17 is 47, plus 3 is 50. Let's make sure it adds up to 200 basically. 40 plus 50 is 90, plus 10 is 100. 5 plus 12 is 17, plus 33 is 50. Okay, we're good that way. 50 plus 50 plus 100 is 200. Let's add across 30 plus 40 plus 5. Hopefully you say that's 75. 17 plus 33 is 50, plus another 50 is 100. 3 plus 12 is 15, plus 10 is 25. So those all look good. Okay. Now, the question is, how do you find the expected counts? All right, here's how we're going to find the expected counts. We're going to take the row total times the column total over the table total. So in this particular cell, okay, for 30, what would assuming that these two variables are independent, we assume they are independent, that's going to be our null hypothesis. All right, for that cell right there, the closer these expected counts, and I'm going to put the expected counts in parentheses, okay, the closer those are to each other, the more this data is independent. Okay, so here's what we're going to do. For this particular cell, we're going to take the row total, which is 75, times the column total, which is 50, and then divide by the total, which is 200. Okay, so I'm going to do it like this. Let's clear real quick. All right, the row total is 75, okay, times the column total, which is 50, over the total, or the table total, which is 200. All right, let's just convert that to a fraction. Oops, not a fraction, a decimal. All right, 18.75. All right, that's what we would expect. All right. Now, what about the next one? Let's just go down. For this cell, we take 100 times 50 and put it over 200. So 100 times 50 divided by 200. All right, that's simply going to be 25. All right. The next one, 25 times 50 divided by 200. It's going to be 6.25. If I were to add these three numbers in green, they should also add up to 50. Okay, and they do. Okay. Now going across here, for this cell, row total 75, column total 100 over 200. So you do 100 times 75 divided by 200. All right, that's 37.5. You take 100 times 100 and divide by 200. And that's 50. Well, you should be able to figure out what this one is without even putting it in a calculator. These two add up to 87.5. It's got to add up to 100. So that one's got to be 12.5. And if you notice this last column, this number matched that number. So the column total here would be the same as the column total there. So for this first one, 75 times 50 divided by 200, it's going to be the same as that, 18.75. For this one, 100 times 50 divided by 200 is going to be the same as that, 25. And on the last one, 25 times 50 divided by 200 is going to be 6 1/4. Okay. So if these things are independent, the closer the actual number is and the expected value, the observed and the expected value are. And the question is, how would you find the chi-square test statistic? Remember what that is? It's the sum of all the observed values minus the expected values squared over the expected values. All right, so you would take, for instance, 30 minus this 18.75, square it, and then divide it by 18.75. And you would do that for each of these 9 cells. Okay. Now, how would you figure out the degrees of freedom? All right. Take the number of rows. You have 1, 2, 3 rows, and subtract 1, times the number of columns, 1, 2, 3, and subtract 1. All right, so that would be 2 times 2. So in this case, there's 4 degrees of freedom. I know I'm kind of jumping ahead and showing you how to get expected counts, but it's important you understand how these numbers come to play. All right. So let's go through our process here, and let's do the full thing. Okay, let's do the full thing. All right. So in step 1, I'm going to make my statement. So my statement are my hypotheses. Okay, so we've got to do these in context. What are the 2 variables here? Okay, we can say anxiety level and need to succeed for freshmen at Woodrock College are independent. Okay. Anxiety level and need to succeed for freshmen at Woodrock College are independent variables. And the alternative is that we could just say that these variables are not independent. We need enough evidence. And as we look at our evidence again, some of these are way off. Okay, some of these numbers are way different than the other ones. Some of them are close, some of them are right on, like this one's right on. Okay, this one's pretty close. That one's pretty close. Here, this one's way off. Yeah, not too far off. This one's a good deal off. Okay. So that's my statement. All right. Next step, we have to do our condition check. All right. So we need to check for random. Okay. So back in the problem here, a random sample of 200 college freshmen. Okay. SRS of 200 freshmen stated. Okay. Independent condition. All right, so I need my capital N to be bigger than 10 times my sample. All right, and my sample is 200, sample size was 200. So we got to make an assumption here. 10 times 200 is 2,000. Assume we have 2,000 freshmen at Woodrock College. Okay. All right. And the last condition, this one's a little different. It's not normal. All right. It's called the expected counts. All right. Now, based on recent things I've heard, it used to be okay as if you were given a table like this to put the expected counts in parentheses. They don't want you to do that anymore. They would actually take off points. Okay. So what you need to do is you need to copy the table. Okay. So anxiety level, high, medium, low. All right. And need to succeed. Okay. High, medium, low. And now what you're actually going to do is you are going to write in these numbers in the parentheses. You actually have to make your own table there. All right. Which kind of sucks, but it's just what I've been told you have to do now. They used to let you put it in parentheses. Now they take off for that. So we don't want to lose points. All right, so I'm just going to copy that data that I made in the previous case. 18.75, 25, 6.25, 37.5, 50, 12.5. You don't have to copy the totals, okay, but you do have to write in the expected counts. 18.75, 25, 6.25. Okay, so what's the actual condition? All of these numbers have to be greater than 5. So I would write all expected counts greater than 5. Now what would happen if one of these was less than 5? Would you stop the test? No, you wouldn't stop the test. You would just say one of the cells had an expected count less than 5, but I'm still going to go on with the calculations. Okay, I've read in different books, different statistics books, as long as no more than about 10% of the expected counts are less than 5, you can still go on. So if I was missing, if one of these was like 4.75, then still 8 out of 9 of my counts are still good. So I would still go on. I would just note it. Okay, I would just note it. All right, so step 3 comes the calculations. All right, so in the calculations, remember our process, SCCDC. Okay, so we got our statement, we got our conditions, now calculations. Give the name of the test. This is a chi-squared test of independence. Okay, now before we calculate anything, pick an alpha level. Okay, pick an alpha level. So we need to give a couple things here. We need to give the chi-squared value. It's also good if you write the formula, the sum of the observed minus the expected squared over the expected. Okay, and we'll get the value here in a second. We should give the p-value, and we should give the degrees of freedom. Okay, now, do I have to calculate each one of these? Do I have to calculate each one of these by hand? No, we have a calculator. So here's how we actually go about doing it with the calculator. Y'all ready for this? All right, it's pretty cool. All right, so just think about the observed counts, not the numbers in parentheses, just the observed counts. And these 9 cells, not the totals. Here's what we're going to do. Go into your matrix menu, which is you have to second first, and then it's the X inverse button. Okay. You have a couple options here. Go over to Edit. Okay. Now, when you go into there, into Matrix A, after you hit, let me go back there because I think I did that very well. So I go to my matrix menu, I'm toggling over to Edit, and I can choose any matrix I want. I'm just going to choose the first one. Okay. Now, when it brings you into that matrix to edit it, at the top, it's asking you for dimensions. How many rows, how many columns? So in this case, I have 3 rows, and I have 3 columns. Okay, so my dimensions are 3 by 3. And all you have to do is enter the observed counts. Okay, but the way it's going to do it, it's going to go 30, then I'm going to hit enter in my calculator. It's going to take me over to the right, to the next cell. So then I enter 40, all right, then I enter 5, and then hit enter. Then 17, then 50, then 33, okay, then 3, then 10, then 12. Okay. So as soon as you do that, go ahead and quit out of there, then go Stat, go over to Tests, and scroll down until you see the chi-square test. Okay. Now this is not the chi-square goodness of fit test, it's the other one. Okay. So in my calculator it's option C, I'm going to hit enter. Okay, so it's asking you a couple things. Where's your observed counts? It's in matrix A. Now, you don't have to put expected counts in there. the calculator is going to calculate those for you, and it will automatically put it wherever you tell it to put it. Okay, it's going to default to matrix B. All you have to do now is go calculate. Okay. It gave us the chi-square test statistic. It gave us the p-value. It gave us the degrees of freedom. Okay. So, my calculations here, I can simply write down the chi-squared is 29.6. All right, think about what this number actually represents. 5.9 times 10 to the negative 6. For our purposes, that's very, very close to 0. That's like 0.00000059. And degrees of freedom is 4. Okay. Now, if you were doing this solely in the calculator, you would do calculations first, and then you would come back to conditions to figure out what these are. You don't have to calculate these by hand. Let me show you what I mean. If I go back under my matrix menu and I go over to Edit, okay, and I go to B and hit Enter, the calculator has calculated these numbers for me. 18.75, 25, 6.25, that's that first column. Okay, 12.5, 50, 37.5, that's this column. And 18.75, 25, 6.25. So I could do this first. I could run it, and then I can go back and I can fill in my expected counts chart. All right, so in step 4, we have to make our decision. All right, well, our p-value is essentially 0. Our alpha is 0.05, so here the p-value is less than the alpha, and when p is low, reject the ho, so we're going to reject the null hypothesis, and then we're going to do our conclusion and state there is sufficient statistical evidence pretty much at any alpha level, but at the alpha equals 0.05 level to conclude that, put it in context, anxiety level and need to succeed for freshmen at Woodrow College are not independent. All right, they're related to each other. They are definitely related to each other. And that's all we're trying to show. There's enough evidence to show that those two variables, the anxiety level and the need to succeed, are not independent. We're going in favor of the alternative hypothesis. All right, enough evidence to reject that. Okay. And go with this. They're not independent. They're associated to one another. All right. So this was a chi-square test of independence. That's independence because it comes from a single population. Okay. So now let's read the next problem. This is example 3. It says, in November of '97, the Gallup organization released the results of a poll on family values. One of the questions asked was, for you personally, do you think it is necessary or not necessary, meaning yes or no, all right, to have a child at some point in your life in order to feel fulfilled? Results from adults in different countries, okay, that's like a key note that people come from different countries. They're going to be coming from, samples come from different populations. All right, is there evidence that the proportion of adults who would give each answer is different for each country? Okay. So let's go through an entire hypothesis test on here. Now, because I'm sampling from different countries, I have more than 2 plus populations. This lets me key into this. This is a chi-square test of homogeneity. Okay. So here's how we can write this. All right. So it's run exactly the same way as independence, but the way we write it has to be a little bit different. Okay. So here's how we can write it with notation. We can say that the row of yes for the US is going to be the same. So the proportion of people in the US who said yes is going to be the same as the row of people who said yes in India. That's going to be equal to the row of people who said yes in Mexico. That's going to equal the same proportion as people that said yes from Canada. Okay. And equal the row of people who said yes in Germany. Okay. So it's kind of like the same thing for independence. If these things are independent, then we would expect roughly the same percentage in each country. Okay. So for example, 46% of people in the US said yes, but 93% in India said yes. Way different. Okay? These would all be roughly about the same if they were independent or if there's no type of association between them. Okay? And it also means that people that said no from the US is going to equal the people who said no from India. These are proportions, not raw counts. Equals the row of no in Mexico. Equals the row of no in Canada. Equals the row of no in Germany. All right. And the last one, proportion of undecided from the US would equal row of undecided from India, would equal row of undecided from Mexico, was the row of undecided from Canada, equals the row of undecided in Germany. My alternative hypothesis is that at least one of the three proportion statements above is not true. Now you could have done HO in words. You could say the proportion of citizens of each country who said yes is equivalent. The proportion of people who said no in each country is equivalent, and the proportion of people who said undecided in each country is equivalent. You don't have to write it with math symbols. You could have wrote it in words. Okay, but the important thing is that you're going to write 3 sentences, okay, because it's got to be the same across for each of these. So we have more than 2 populations. The response is the variable of interest, and there's 3 categories of response: yes, no, and undecided. So this is the statement. 2 different ways to do it. All right. So now we have to do our condition check. All right. However, we have populations from 1, 2, 3, 4, 5 countries. Okay. So we have to make some assumptions. Okay. Let's see if the random condition is met, or if they told us that it was random. Okay. Says it's a result on a poll. All right. Doesn't tell me anything about random, so I'm going to assume a SRS of adults was conducted in each country. Independence condition, n is greater than 10n. Okay. Now, what's the sample size? Sample size in each country was 1,000. Okay, so I can just do 10 times 1,000, which would be 10,000. All right, and I can say clearly there are at least 10,000 adults in each country. Now, what about if they weren't all the same? Okay. If they weren't all the same, take the biggest number, the biggest sample size from each country, multiply it by 10, and there's still going to be that many people. Okay, in all those countries. Okay, in the US, there's what, 320 million people, and of those, probably 270 million of them are adults. You're going to be okay there. All right. And the last one is the expected counts. We're going to come back to this one. Okay, but we are going to start by making a table. All right, just like the table I see above. And I'm going to plug in, when I actually run my calculations, that's going to calculate the expected counts for me. And I'll come back to this. So let's go on to the next step, step 3, which are our calculations. Tell the reader what kind of test you're performing. This is a chi-squared test of homogeneity. Okay, and let's pick an alpha. All right, let's pick an alpha of 0.05. All right, I personally like to write the formula. Chi-squared is the sum of observed minus expected squared over expected, but I'm going to let my calculator do the hard work and find the p-value and find the degrees of freedom. Okay. So we're going to enter those counts into a matrix. Okay, so I'm going to go under my matrix menu. I go over to edit. I just like to choose A. How many rows? 1, 2, 3. How many columns? 1, 2, 3, 4, 5. So this is going to be a 3 by 5. I'm just going to type in the numbers going across. 460, 930, 610, 590, 490, and 510, 510, 60, 380, 370, 450. And 30, 10, 10, 40, and 60. I'm going to quit out of there. I'm going to run my test, which is just the chi-square test. All right, my observed counts are in A. The calculator is going to put the expected into B, and we're going to calculate. All right, so a huge chi-square number. All right. So that chi-square number for my calculator is 628.075. It tells me the p-value is 0, such a small area. All right, and the degrees of freedom are 8. If you want to think about how that happened, all right, 3 rows minus 1 is 2, 5 columns minus 1 is 4, 2 times 4 is 8. All right, now how am I going to get the expected counts? Go backwards. Go under matrix, go to edit, and look at B. These are the expected counts. So I'm just going to copy these over. All right, so the expected counts are 616, 354, 30. And you'll just have to trust me, I'm copying them correctly. All right, 616, 354, 30. If you notice here, all right, all the column totals are the same. So in this row total for everything going across, you'd use 3080, and looking down at each column, you get 1000. So all these numbers across are going to be the same. They're all going to be 616. Okay. And same thing across here. Remember, to get expected counts, you do row total times column total, but all the column totals are the same. So those would all be 354 going across. Okay, and likewise for the last one. Row total is 150, column total 1,000. So it would do 150 times 1,000 divided by 5,000. And that's where they're getting 30. Okay, so it does it for us. So we can go back to that last condition. All of these numbers are greater than 5. So I can say all expected counts greater than 5. Greater than or equal to 5. Okay, so the conditions work. We've done statement, conditions, calculations. Now we do decision. All right. So our p-value was 0, which is clearly less than our alpha, which is 0.05. So 0 is less than 0.05. So we're going to reject the null hypothesis. Okay. We could write step 5, the conclusion. There is sufficient statistical evidence at the 0.05 level to conclude that, if you need help to figure out what to write, go back into a question itself, that the proportion of adults who would give each answer is different for each country. We can say it just like that. Okay. That the proportion of adults who would give each answer is different for each country. I know I have really sloppy handwriting. That's why I'm talking a lot. So, right, that's your conclusion. Right. It's run exactly the same way as a chi-square test of independence. The only difference is the hypotheses are phrased a little bit different way. But everything else is exactly the same, with the exception of, all right, when you do your population size, you got to do that for all of them if they're different, or just take the biggest one. Okay? But you want to say there's at least that many adults in each country, because there's more than one population. Same thing here. Assume simple random sample is conducted in each country. I had to make that assumption so we could go on. That's what they want you to do. Okay, let's keep going. Let's do some more. All right. It says Buddies is a volunteer social service that works with disadvantaged children. Adults 18 years and older volunteer from 1 to 6 hours per week to take a disadvantaged child to the zoo, to a museum, to a movie, or some other activity. The program recruits adults from 3 main groups: college students, non-students living in the inner city, and non-students living in the suburbs. A random sample of adult volunteers gave the following information. Is there an association between the number of hours volunteered and the type of volunteer? All right, so association is like independence. All right, that's another way to phrase it. Is there, are these variables independent? So what are the variables? First off, the data comes from a single population. All right, so that keys me into chi-squared test of independence. All right, so here's one variable. It's one categorical variable. All right, place where they live, where the volunteer lives, and the number of hours volunteered. Now that may seem like a quantitative variable to you, but it's actually a range. So it's 1 to 2. So that's why it's a category instead of a quantity. All right, so these are 2 different variables: the hours that they volunteer and the place where the volunteer lives. Okay, so let's go through our process. All right, number 1, there are hypotheses. Okay. So the null hypothesis is that the place where the volunteer lives and the hours volunteered are independent. And we assume that they are independent. We need proof that they're not. All right. So the alternative is that these variables I even underline them. The variables are not independent. Now, when your test actually lists out the variables, go ahead and say this whole thing again, but just say are not independent. Okay? So that was step one. Step two, we have to do our condition check. All right. Now, to do some of the condition check, we probably should make some totals here for ourselves. Okay, so let's just go ahead and add down here. So 115 plus 88 plus 95. So that's 298. 93 plus 150 plus 133 is 376. Okay, 47 plus 56 plus 60 is 163. If I add across, 115 plus 93 plus 47, 255. 88 plus 150 plus 56, 294. 95 plus 133 plus 60, it's 288. If I add down, 255 plus 294 is 288. You get 837. Let's verify that's correct by adding across 298 plus 376 plus 163. Okay, good. I got the same number, 837. So conditions, we need 3 of them. Random. Okay. Right. Assume the SRS of 837 volunteers was taken. It never told me that it was random. The problem did not tell me it was random. Oh, never mind. Yeah, it did. Random sample of adult volunteers. Okay. Sorry, didn't read it. Random sample of adult volunteers stated in problem. All right, independent. N is greater than or equal to 10n. All right, this is why it was important to find the sum there. So 10 times 837. This one might be a little bit of a stretch. 8,370. All right, are there that many volunteers in this organization? That's a lot. So we have to make the assumption. Assume that there are at least 8,370 volunteers in this buddies organization. And there might be. I mean, it might be a big city. So, and the last thing we got to check, but we're going to come back to, is the expected counts condition. Okay. So I'm going to copy the table above, but I'm going to leave it blank. So we're going to say hours volunteered. Okay. 1 to 2, 3 to 4, 5 to 6. And over here, We're just going to do college, student, inner city resident, suburban resident. The whole purpose of making this table is now to show the expected counts, assuming they are independent. Those variables are independent. All right. So we're going to go to calculations next. So we're going to go ahead and put our data into matrix A. So we're going to go over to edit. This is going to be a 3 by 3, 3 rows, 3 columns. And I'm just going to enter the data, 115, 93, 47. Remember, observed. All right, not the totals. 88, 150, 56, 95, 133, 60. Quit out of there. Now let's just run our calculations. Go to your tests, chi-square test, A, B, calculate. Over here, we can do our calculations. All right, let's assume the alpha is 0.05. All right, this is the chi-square test of independence. All right, chi-squared equals the sum of observed minus expected squared over expected. My calculator just told me that it's 16.70. The p-value is 0.0022. The degrees of freedom is going to be 4. 3 minus 1 times another 3 minus 1. 3 columns, 3 rows, subtract 1 from each and multiply. So that value is important. That value is important. That value is important. Okay, let's go ahead back to matrix B now to get the expected counts. Over to edit, choose option 2 for B. All right, now this is some decimal, that's okay. All right, so I'll just go ahead and copy this over from my calculator. All right, that looked like 90.79, 104.67, 102.54, 114.55, 132.07, 129.38, 49.66, 57.25, 56.09. So there's some differences. We got 115. If these were all truly independent, right? This is if these variables were independent. All right, we would have gotten these numbers. Like if they were exactly independent, if there was absolutely no association between them, between those two variables. All right. So what do you notice about all these expected counts? They're all greater than 5, so I'm going to write that. All expected counts greater than or equal to 5, which is one of your conditions. We're doing calculations, so decision, the p-value is 0.002, the alpha is 0.05, so it's less than alpha, because 0.002 is less than 0.05. The p is low, reject the ho, so we're going to reject the ho. All right, then we're going to write a conclusion. Conclusion, decision. All right, there is sufficient statistical evidence at the alpha equals 0.05 level to conclude that the place where the volunteer lives and the category of hours volunteered not independent. They're not independent. So one affects the other. Instead of writing the words not independent, you could say are associated. There's some relationship. I don't like to do it that way. I just like to say not independent, which means there is some dependence. This and this affects this, or this affects that. Okay. All right. So, as I know you're probably sick of this, we got a few more examples, but we're just going to go over them. It says the AP Statistics exam was first administered in May 1997. That was a year before I took it. All right, students' papers are graded on a scale of 1 to 5, with 5 being the highest score. Over 7,600 students took the exam the first year with the following distribution of scores. Okay, so these are actually observed scores here. All right. It says a random sample of students who took the exam. Well, this isn't the number, this is the percent of the scores, who scored a 5, 4, 3, 2, 1. All right. It says a random sample of students who took the exam in 2017 had the following distribution of grades. Okay. This is raw counts. Okay, so should have made this a little bit more clear. This is percent, even though it says percent there. Okay. This is raw number. Okay, so this is what we know as observed data. All right. So it doesn't give us a total, and it does tell me it's a random sample. Let's go ahead and add these numbers together. So 167 plus 158 plus 101 plus 79 plus 30. All right, looks like 535. 535. All right. So let's read the question. It says, is the distribution of scores for this sample significantly different from the distribution of scores for all students who took the inaugural exam? Okay, so they're saying the people that got 5s in 2017, is it roughly about the same as the people that got 5s in May 1997, 20 years earlier? Okay, so do these percentages still correlate to the same percentages these would be? Interesting. All right, so let's think about what kind of data we have. We have data here. This is our actual data. Okay, so it's coming from one population, and we're only measuring one variable, the variable being the score that they got on the AP exam. All right, so this keys me in that this is a chi-squared Goff test. It's a goodness of fit test. Okay, so let's go through it. All right, let's do this whole thing. Let's go through the whole test. So this is a chi-squared Goff test. All right, so what are my hypotheses? What are my hypotheses? All right, well, actually, don't call it hypothesis, call it statement, sorry. It's been a long day. All right, so my hypothesis is that the score distribution for AP Stats in 2017 is the same as 1997. That'll be my null hypothesis, and my alternative hypothesis is that at least one proportion from 2017 is not the same as 1997. So that's how we would do that. All right, step 2, we have to do our condition check. Okay, so random. Down here at the bottom, a random sample of students, so we're good. Random sample of 2017 AP students. I'm just being explicit saying, okay, I'm looking at the students who took it in 2017, because that's where the sample's coming from there. All right, independent, n greater than 10n. All right, our sample size, that was this 535. That was the sample size right down there, bottom. All right, so that's the n, 535. N is greater than 5350. So we're going to assume at least 5,350 AP stats tests given in 2017. And expected counts. Okay. How are we going to find expected counts? Well, this is a golf test, so I don't put it in a matrix. I don't put the observed counts in a matrix. I put them in a list, and you have to put them in a list. So maybe list 1 might just be a good way to give the scores that are possible. So 5, 4, 3, 2, 1. Okay. Then let's put our observed counts in list 2. So I had 167 students make a 5, 158 made a 4, 101 made a 3. I'm just putting this in the calculator. 79 made a 2. 30 made a 1. All right. Then I could put the hypothesized proportion. Okay, and now I'm just going to put it in L5. For some reason I don't know where list 3 went, but I'm just going to put it in list 5. So 15.3%, I'm just going to type in as 0.153, 22%, 24.8%, 19.8%, 18.1%. Okay, now really before we go on, we really should check to make sure those add up to 100%. So I'm just going to quit out of here. Add up 15.3 plus 22 plus 24.8 plus 19.8 plus 18.1. All right, cool. Add it up to 100%. That's good. That's important. All right. Now, how am I going to get the expected number? How am I going to get this E here? All right. Well, I'm going to go back in my list here. These are the hypothesized percentages. Okay. So what I'm going to do, I'm going to go up to the top of the list and I'm going to say, okay, take those percentages that are in list 5 and let's multiply it times the sample size, which is 535. And there we go. These are the expected number. If 2017 was the same as 1997, we would expect 15.3% of the 535 to give 5s. So the expected numbers are as follows. Okay, so 81.86 roughly, 117.7, 132.68, 105.93, and 96.84. Right. So if these percentages really were the same, All right, if the distributions were the same, we would expect that many people, but we observe much more than that. Same thing here. Here it's a little bit less. We observe a little bit less than we expect. Same thing here, it's a little bit less. Here it's a lot less than we expect. Okay. So that's why a lot of teachers now think that stats is easier than it used to be, because this is the way they used to do it. Okay. This is how they used to do it. That used to be really hard. Not so hard anymore. All right, so how are we going to actually do our expected counts here? There it is right there. All of these numbers are greater than 5. So you can kind of copy this chart, expected counts. I could say score of 5, 4, 3, 2, 1. Expected, I'm just copying the expected data. 81.86, 117.7, 132.68, 105.93. Should have given myself some more room. And then 96.84, and all expected counts greater than or equal to 5. All right, so we'll go on to calculations here. So this is a chi-squared goodness of fit test. Let's pick an alpha of 0.05. All right, I like to write the formula. To find the chi-squared, we're going to sum observed minus expected squared over expected. So my observed counts are in L2. My expected counts are in L6. So I'm going to go stat. I'm going to go over to tests. And I'm going to pick the chi-square goodness of fit test. Okay. So my observed are in L2. My expected are in L6. But we also have to denote the degrees of freedom. So how do we find degrees of freedom on a goodness of fit? How many different categories of scores do you have? 1, 2, 3, 4, 5. So it's 5 minus 1. It's the number of categories minus 1. So 4 degrees of freedom here. You got to know to enter that. Calculate it. So the chi-square test statistic is 162.91. 162.91 right there. And degrees of freedom here. Gives me the p-value on the calculator. Really, really small. 3.48 times 10 to the negative 34, which is approximately equal to 0. Right. What you'll notice on chi-square test, most of the time you're going to get a p-value less than alpha. It's very rare that you don't. Okay. So, decision, that p-value is essentially 0, which is less than the alpha, which we picked of 0.05. So the p is low, we're going to reject the O. And our conclusion, usually in the problem it helps me write the conclusion, is the distribution of scores for this sample significantly different from the distribution of scores for all students who took the inaugural exam. So we can say there is sufficient statistical evidence at the alpha equals 0.05 level to conclude that the distribution, that the score distribution of AP Stats exams differs from 2017 and 1997. There's sufficient statistical evidence at the alpha equals 0.05 level to conclude that the score distribution of AP Stats exams differs from the years 2017 and 1997. It's easier nowadays. So this has been kind of a longer video. I'm going to save this one. We can do this one in class, or you can try it on your own. But they tell you that the hypothesize proportions for all these different colors. For peanut M&Ms, here's your observed counts. You can figure out the expected counts. This is another chi-squared GOF test if you wanted to do it. So, I'm tired of talking, so I'm going to stop there.